All right, welcome back. Time to keep moving forward in our, in our workflow here of running a model. In this case, it's a numerical weather prediction model. So just flashing back here to this slide here that had mathematical models. Well, it's time to make our prognosis. Prognosis, a tricky word there. Just to pull up a Google definition of prognosis, I like the part that I highlighted in red there. It's a forecast of the likely outcome of a situation. Oh, doctor, I have chest pains. What's my prognosis? You're going to live. Okay, the prognosis is you're going to live. The prognosis here is the forecast of the likely outcome of the situation. We now have a situation. We have the assimilated data that we call the analysis, and we're going to start applying the physics of the atmosphere to that information in the form of a numerical model. All right, now remember what we said is that a numerical weather prediction model, it's a type of mathematical model, but specifically it's using the actual physics. The equations that we're applying are things like the first law of thermodynamics or Newton's second law or whatever, the physics of the situation to simulate how things like temperature, pressure, winds, etc. are going to be changing in each of those boxes here. So just like we could have been following this rocket, just to flash back to a previous slide here, where we could have a numerical model of this rocket and at each time figure out what forces were acting on the rocket and therefore by F equals ma what its acceleration was, and then based on its current velocity we could talk about how its velocity was changing due to that acceleration. That would be a lovely, lovely example of a numerical model. Well, now we're going to do that, again just flashing back to a slide we've seen before, we're going to do that instead to each of these boxes. The boxes themselves aren't going to be moving. I mean, the boxes are part of the geography of the model. Air can flow through these boxes, but we're saying how is the temperature inside that box going to change? Or how are the winds inside that box going to change? And how is the pressure, and how is the humidity, and how is the cloud cover, and so on in those boxes. Again, recognizing that those, in the real world, model resolution, might be on the order of a few kilometers across each of those boxes, not literally hundreds of kilometers the way it shows in this diagram here. So apparently, in order to run a numerical model of the atmosphere, we're going to need to know the actual equations that describe how the atmosphere is changing. Now, I'm going to tell you, all those equations are going to be really horrible. The good news is we are not even going to look at the equations themselves. We're just going to real quick go through what they are. Honestly, between this class and your physics classes and so on, you've actually seen all these equations before. You might not have seen them in the full form with all of the nifty things that atmospheric scientists take into consideration, but they're all going to be old friends once you actually get going on it. The physics of the atmosphere is going to be described by merely 7 equations. There are 7 equations that describe the physics of how things change in the atmosphere. They have a name. It's called the 7 primitive equations. I don't honestly know what the word primitive means in this context. I've never seen it described. Even when I was a student, I remember asking, and the teacher was like, yeah, don't ask difficult questions. So I don't know why they're called the primitive equations, but they are just 7 equations. It's a system of 7 equations that are describing how the winds will change, how the pressure will change, how the temperature will change, how any of the properties of the atmosphere will change. It's a system of 7 equations, and all of those equations are horrible. 2 of the equations are actually old friends to us in this class. They're equations that are about the relationship between force and the wind. And we actually saw forms of these equations way back when we learned about like pressure gradient force, Coriolis force, centrifugal force, gravity, etc. They're actually just ways of saying Newton's second law. Okay, force equals mass times acceleration. So if we know the force acting on some volume of air, we know that air was mass, so force equals mass times acceleration, we can know how the air is changing. Now in practice it takes 2 equations to do that, because one will be in the U or west to east direction, and one will be for the V or south to north direction of the wind. Writing them out is by no means simple. It's a complex, they're what are they, partial differential equations. They're a mess. They exist. We can think about them. A third equation, that is of our 7 primitive equations, is one that connects how pressure, temperature, and density are related. This one's actually not so bad. It's called the ideal gas law. In fact, if you took like Introduction to Meteorology, we talked about P equals rho RT. Pressure equals density times the gas constant rho times T. I think we even had like one slide about that way back earlier in this course. That one's not so bad at all. There's another equation that describes spin in the atmosphere. Spin is an important concept. You can understand spin is important in the atmosphere if you think about like hurricanes, cyclones, anticyclones, dust devils, tornadoes. Spin is important. It's a property that is, it's a conserved property, like conservation of angular momentum and so on. Turns out that in the context of fluid mechanics, and the atmosphere is a fluid, it flows, there is an equation called the vorticity equation that actually describes the physics of how spin, and the particular measure of spin that we're using here is vorticity. That might be a concept you are or are not familiar with, but vorticity is a measure of spin in a fluid. The vorticity equation can then be used to describe how spin is going to be changing in the atmosphere, which is going to be important for, development and changes in the winds, development of certain kinds of storm systems, etc. So our fourth equation is the so-called vorticity equation. Again, it's a mess. It has all kinds of horrid mathematical operators in it. You're glad you don't even have to look at that thing. 5. The fifth of the 7 primitive equations is all about the ways in which temperature can change. It's going to have a left-hand side that's something like change in temperature with respect to time equals, and then a horrible right-hand side that is really the first law of thermodynamics. If you're a survivor of general physics, if you're a survivor of general chemistry, heck, if you're a survivor of high school physics, if you're a survivor of high school chemistry, at some point you got exposed to the first law of thermodynamics, which is all about changes in temperature as you add and remove heat by various processes, be that radiation or conduction or latent heat release or expansion or compression of air particles or chemical reactions or whatever. This is a big equation, but it's just an equation. Computers like equations. Computers are good at equations. We don't need to worry about the fact that it's a big equation. Who cares? It's the first law of thermodynamics. We need to have some kind of law. We had already a law that was about the U wind and about the V wind, but we also need a law that's about the vertical wind. As it happens, there is a very good equation to describe how vertical winds are created in the atmosphere and how they change. It's called the continuity equation. In fact, I believe continuity was actually a term that we used in an earlier module. Again, we don't need to get bogged down in the details, but in general, the continuity equation is about how, like, when air comes together at the surface, when there's convergence, the air will rise, and when the air sinks at near the surface, it spreads out, and so on. It's all about creation of vertical motion in the atmosphere. It's actually a relatively simple equation to write out, and then the math gets really complicated. Then there's one last primitive equation, and it's about water. It's known as the conservation of water. Remember, conservation, conserved quantity, that's a term we've seen over and over again. Conservation means, like, as in we aren't creating or destroying. Well, we have a certain amount of water in our Earth, atmosphere, land, ocean system, and we aren't creating or destroying it. So, for example, when in your model you have water vapor in the atmosphere condensing into liquid water drops and dropping them to the ground, well, that has to reduce the amount of water vapor in the atmosphere. On the other hand, it has to increase the amount of water vapor that the model sees on the ground, and so on. You have to have this total amount of kilograms of water constant. It just is changing phase between solids and liquids and gases. Again, there's equations that describe that. Not particularly pleasant equations, but equations. Again, models don't care. They don't care about whether the equations are hard, they're just computers. So we have these 7 primitive equations that I have here tossed together in this green box, and honestly, 6 out of the 7 of them are horrible, and frankly, even the one that was the ideal gas law, the number 3 on there, frankly, even it's horribly nonlinear. They are not a simple thing to solve. They actually take an enormous amount of work to solve. None of these are the kinds of things you could just plug numbers in and get an answer to. All of these involve numerical iteration, where the computer makes a guess as to what the answer is, can figure out how far off it is, it can estimate how far off it is from the right answer, then comes up with a second guess, this iterative process. So it may have to do enormous amounts of math to solve one of these equations, and it actually has to simultaneously solve 7 of these equations, which is fairly horrible. Plus, each of these equations only solves for like the temperature or the pressure or the wind or whatever, humidity or cloud cover or whatever at a specific time. A small step forward in the future. How big of a time we're talking about? Like maybe 10 seconds into the future. Well, what good is a forecast for 10 seconds from now? All you're going to be able to do is use that as an input for 10 seconds to run the model again and again and again and again. And if you run it 6 times, you got a forecast for a minute from now. If you run it 60 times that much, it'll be a forecast for an hour from now. Oh my. This looks like a lot of math. Yep. More importantly, all of these equations only solve for the temperature and the pressure and the winds and so on at one grid point, at one of those boxes. You've got millions of those grid points spread out all over your model domain, like over the whole Earth or whatever here. Oh, so we got to do this like millions and millions of times just to get a forecast for like 10 seconds from now? Yeah. Yeah. This little business of how the model moves in these little steps of time forward, that's called a time step. The time step for a typical model is something like 10 seconds. It can be as little as 1 second. It can be, it could be awfully little. It can be as much as maybe a minute or so, depending on exactly some factors. There's a whole business of deciding how big your model's time step should be. So what you do is you're going to be applying these 7 primitive equations, spending enormous amounts of work on your supercomputer or whatever to solve them. You get a forecast for like 10 seconds in the future, and then you just got to keep doing it over and over again until you've done it enough times that, now you have a 24-hour forecast. Or you've done it enough times that now you have a 48-hour forecast. Or you've done it enough times that you have a 72-hour forecast. Or if you're doing climate models, that you have a forecast for what the weather's going to be, what the state of the atmosphere is at the end of this century. Do you think this is going to be a lot of computer power? Yep. That's why, remember we told you, you had to make sure that you have the resources to run this thing. I mean, you're going to need a pretty big computer. If you're trying to make a forecast of what the weather's going to do 24 hours from now, you don't want your model to take more than 24 hours to make that forecast. You need your computers to be able to, be powerful enough that they can do all this math in, say, 2 or 3 hours so that you can make a forecast in time for people to use that information 24 hours from now. It's a big job. It takes a fairly big computer. You can run a numerical weather prediction model on a PC or a Mac. But you probably can't run it like as in to make a forecast for 24 hours from now. You can run it in that way like a research setting. For example, if you wanted to study a particular storm system, you can get the model running on your PC and run it and give it initial conditions. But it might take a week of the computer chugging on the numbers to make the forecast for 24 hours from now. So obviously in the real world, like if you're making forecasts at a power company or for the National Center for Environmental Protection, Environmental Prediction, or the National Weather Service, or the UK Met Office, or the European Center for Medium Range Weather Forecast, all these places around the world that run these models, you need a supercomputer so that this thing can get done doing enormous amounts of calculations in like 3 hours, not like 3 weeks or something like that. And in the process of running, this thing is going to create enormous amounts of output. A simple numerical weather prediction model that you can download and run on your PC or something like that produces many gigabytes of output. In one of my classes, we used to run a model called the WRF, and every simulation took about 10 gig of disk space or something like that. It produces enormous amounts of output. Even a relatively, I think that was a 72-hour model run. It took the model about 4 or 5 days to forecast 72 hours of how the weather was going to change, and then we studied it. Literally like 10 gigabytes of data. Is that a lot? Well, kind of. Yeah, it's kind of a lot. On the other hand, it's manageable. You just have to have enough disk space, and you have to have software to know what to do with it, and so on. It's going to have created, at every one of those grid points, it's going to have saved things like what the temperature, the pressure, the winds, the cloud cover are, at whatever times you wanted. Like maybe you wanted that information once an hour. So you made a 72-hour forecast, and once every hour you created files of this stuff. So you've got 72 sets of files for every grid point all the way around the world. I mean, all of a sudden you can see you're filling up your hard drive with enormous amounts of output. Some of that stuff is actually what you're trying to forecast, like maps of the temperature. Other ones are going to be maybe more basic information, like what are the forces acting on each volume of air at that time. So maybe you could do some science then and do some calculations. Or maybe you also just want the visual output. I mean, every model also creates all these graphs and so on of what you can look through to just see what the model did. I mean, after completing the forecast, most model systems actually are set up to just go ahead and create graphics of standard meteorological products that your forecaster is going to want to see. So like this is the ugly web page for a particular model. I think this is GFS. GFS stands for the Global Forecast System. It's one of the models that forecasters use, and you can actually go through here and pick through and get plots of what the model thought the atmosphere was doing at a particular time and simulating, and a professional meteorologist would be able to look through here and start coming up with ideas about how warm it would be, or how windy it would be, how much electrical load you'd have, how much electrical yield you'd have from your wind farm, whatever. That's all part of the post-processing. I mean, this took computer power to do it. This took storage space to store on the computer. It took a server to, put this on a website and you could access it and so on. In general, most models produce that kind of stuff, as well, that kind of graphical output, as well as the raw numbers that like you might use if you were doing calculations on the output or something. Also, a number of third parties do it. Like this just happens to be Unisys's website, where they download the raw data from the federal government's models, like at the National Center for Environmental Prediction and so on, and then they produce plots that they find useful for their customers. Be that power customers, or Unisys does a lot of work for airlines, like they help with forecasting flight routes and stuff like that. So they have products that work better, they produce these graphical outputs. But no matter what, I mean, this is an enormous amounts of work to set this all up so that this is all operational when the models run. There's also the whole business of, if you just get the raw output of the numbers, there's all kinds of specialized weather software that you can learn to use that creates custom plots. Like these things here happen to be made using a custom weather visualization software package called GEMPACK, and I don't remember exactly what's being visualized right here, but this is just two different plots they made, like comparing one model run to another using GEMPACK. Okay, kind of thing that like you would be trained how to use if you were working in the wind power industry, or working for an airline planning flight routes and so on like that. Man, these models have so many steps and so many things going on. Before we move forward and learn about another challenge in numerical weather prediction, let's answer 3 more quick questions. Question 4. The processes that can result in changes in the temperature at a given grid point are summarized in a primitive equation known as the ideal gas law, Newton's second law, the first law of thermodynamics, or Snell's law. Which of these is the correct name for the equation that describes the main ways in which temperature can be changed? Make a choice from those 4 options, get a little feedback before we move on to question 5.